Hello everyone. Today we are going to be working on a deep NLP model. Specifically, we are going to be working with Bert. Now this is part of a small Kaggle mini-series I'm doing. You can watch the first episode if you want about an exploratory data analysis, or you could start here if you just want to start with the model. Essentially, I'm going to be using the skills I learned in my undergrad doing research and also at companies like Amazon and Google as a software and ML engineer to show you how to get going with Kaggle, or even if you're not interested in Kaggle, just how to use models like Bert and get started on problems like this. If you are interested in videos like this and other sorts of things on ML and AI, I do a lot of stuff like this, so do consider subscribing. But either way, let's get to it. So I've already opened up a Kaggle notebook, and this is essentially a challenge, if you didn't see the first episode, where we are given an excerpt and we need to determine the difficulty of the excerpt, and we have some labeled data. So we are going to need to do some imports and install some data sets first. I don't want to spend too long on this though, because it's a bit boring and it's something you can probably figure out yourself, but we need to install data sets. The issue though is that when we are doing this challenge, we have to do it offline. It's just one of the stipulations by Kaggle. So instead we have to download these manually. So this looks a little bit bad. Let's also go ahead and add the actual data to the offline notebook. So I think, what is it going to be? We need Huggingface Bert. Let's see if we can find this. I think, which one of these is, I think this is it. It's essentially, that's not what I meant to do. Let's undo this. Yeah, so let's add that. And then the other one we're going to want to add is Hugging Faces. And this will essentially get us all the libraries and pre-trained models that we need to work with. There we go. So we got those. Now we can go ahead and install them. Really, this is just installing the data set so we can format our data set correctly. I'm also going to set this environment variable, and let me go ahead and expand this. This environment variable want to be disabled. By default, what we're going to be using uses this library. I don't want to use it, so don't mind that either though. And then quickly get our imports in. So NumPy, Matplotlib, Seaborn, and then we're also going to be using transformers. So Hugging Face is essentially a library you can use for deep NLP. It does tokenization. You can load in pre-trained models. It does lots of training for you, loading in data sets, all sorts of awesome stuff. So the combination of Torch and Hugging Face Transformers is what we will be using. So let's go ahead and import all that. Now I'm going to just copy over loading the data because we did the exact same thing in the past video. Oh no, that was very quick. Give me 1 second, I'll be right back. Okay guys, I'm back. I don't know what the issue was earlier, but I did just realize we forgot to add the actual training data. So let's go ahead and add that competition data, common lit readability, and run this again. So now we can actually get started. I also switched this onto a GPU because we will be using that. You can change it right here on the right. But yeah. So we have the data loaded up. We're not going to look at it because we've already taken a look in the last video. So what we want to do is load up our model and our tokenizer from Hugging Face. So to do that, we can specify the directory of the model. So we can see up here on the right, go here. We have all these to work from. We are just going to use the Bert base case, one of these basic ones. And then we can use these from pre-trained methods right here to load in the tokenizer and the model. So when we load this up, if we actually want to print out the model, this might take a second, but we should actually be able to see everything that's going on inside the model, see all the layers and everything. This should be fine. Yeah, so we can see all of the layers, and you might have noticed that even though this is a regression task, right? It's a regression task because we're trying to figure out the difficulty, which is a continuous value. We have this Bert for sequence classification. So I am using this, it's the closest thing to what we have. And the reason I'm doing that is, it's just the closest thing we have. So we do need to edit this because if we look at the output right here, where are we? Yep. So in features that, but the out features is 2 for 2 different classes, right? But we just want 1 output. So let's go ahead and modify that. This is called classifier is the layer. So with a simple line, model.classifier equals, we're just going to change the linear layer to 768 in and 1 out. Now this should change that. The other thing we need to do is there is another parameter for the model that has the number of labels, which is just going to be 1 now. And this is used in the training and stuff to reference this number right here. So let's run that. And if we reprint out the model, we should now be able to see the classifier is one feature out. There we go. So set that up for our regression. Very nice. Let's go ahead and run some test data through this really quick to make sure that this is going to work. So the first thing we want to do is get our inputs and our labels. So here is an example I pulled from the Huggingface website. You can see, you can tell it's not my code because I'm not using single quotations. Input. So this is just the tokenizer. We pass in this value, return it as a PyTorch, I think is what this stands for. And then the label will just be some random number, we'll say 0. So we set those up. And the next thing we want to do is include the labels in this inputs. The inputs, if we actually print this out, it's a dictionary, right, of tensors. So the input ID, the token types, the attention mask, all this stuff. We are just going to add the labels into this dictionary so we can pass them in all as one object. You don't need to do this, but it makes life a little bit easier. So if we just do outputs equals model and pass in the inputs, we should be able to get, there we go, no crashing, awesome, some outputs. So that's working. So we can go ahead and print these out. Specifically, what we'll be interested in is the loss in the logits, because that is what we will be using for training. And we can see we get numbers out for both of them, which means everything is working. Awesome. So let's comment this out. We won't actually need this. I just want to do a test run to show you how we pass some data through this very simply. What we need to do now, though, is load in our data sets. We're going to be using the datasets library from Hugging Face, which should make this a lot easier. So all we have to do is call this a load dataset function, say it's a CSV file, and then pass in the specific file path, which we already had earlier. So once we do this, we should be able to say train data sets. Now, there's only one, but it always gives it to you as a list. So that is why I say data sets. A little longer to load than I thought, but once we do load that, we can print it out. We can maybe move on for now. The next thing we're going to need is a tokenization function. So the tokenization function, kind of like we had up here, will take in some variable and then tokenize it into all these different pieces. We are going to make some slight modifications though, so let me show you what those are. This is our own tokenization function. And what we do is we return, oh, there we go. Sorry, just back on this. So it looks like it printed out the data set, loaded all 2,834 with all the proper features. Looks good, looks good. So back to this tokenization function. We have a tokenizer now, right? The tokenizer, same thing we used up here, tokenizer. So here we just pass in the string. Here, we are going to be extracting the excerpt from our data. How do I know it's the excerpt? If I print out the train data sets again, you can see we have all these features. The excerpt is the one we want. I think we can even index this, right? Oh, no, we can't. Never mind. Completely ignore me. But the excerpt is the passage, so that's what we're going to be tokenizing. We're going to be setting the padding to max length. This means it will just pad with pad tokens up until the maximum length. What is the maximum length? That is 512. How do I know that? If we do tokenizer dot, I think something like max. Oh, it doesn't want to load for me right now. Max model input sizes. We can see for Bert base cased, it's 512. And this is just the default setting. You can mess around with this if you want. And then we'll truncate it too. So if it's over 512 tokens, well, then we can cut some off. But that will be our tokenization function. What we can do now is a few things. I'm just going to copy this over. It's the boring, the boring data set stuff. We can go through this pretty quickly. So the train data sets, essentially what we're doing is we're applying the tokenize function to everything. We're then removing the unnecessary columns, the ID, this URL nonsense, basically everything. We're also reserving, taking away excerpt because at this point, the input IDs, the tokenized format is already in this data set now. We don't need the raw excerpt anymore. So we remove all those and then we rename target to labels because the pre-training you'll see, if you were to get to not the pre-training, there's the normal training and the fine tuning. When you get to it, it likes to have these be called labels. You'll see that when we get there. I do seed it with 42 because the meaning of life, and also so this is easily reproducible. And then we do the same thing for the test data set essentially. So that should get our data all up and running. It might take a second to tokenize. If we actually want to, though, we should print out ftrain datasets. Oh, let's get in there. Well, once this finishes, let's make sure that we have all the right features. We should have the input IDs, the attention masks, attention mask, input IDs, labels, and token type IDs. That's everything we need. The labels are the output, and everything else are the inputs we're going to have to this model. So we've got all of our data formatted. Now we can go ahead and actually start doing the training. Almost. We actually do need to do one more thing, and that's splitting into not just our training and test, but our train, eval, and test data. So very quickly, let's say we want to reserve 10% of our data for evaluation. What we can do is get the length of the train data set, and then from that, calculate how many samples will be in training. So that will be 2,550 in our train set. Now we can very quickly select that many samples from each of these, or for each of these. So for the train data set, we'll select everything in the range of in train. So that's those 2,500 or so examples. Then eval data set, we will take everything after that. So now that we have these, we should be able to do length of ftrain data set and see, yep. And then if we do eval, we should have only, a little less than 10% of that. Yep, 284. Awesome. So that's 10% of the original data set. The eval data set we will be using for evaluating as we go. That is the difference between the test and the train. The evaluation data set is every single epoch or every so many steps while we're doing our training. We want to see how we're doing to make sure that we're not overfitting. Speaking of not overfitting, we're going to want to calculate some metric. Metrics are important to measure how we're doing. And the one we will be calculating is the one used for the challenge. So I don't have it open here, but if you go back to the challenge, what you'll see is they're using the metric RMSE on the leaderboards. This is root mean squared error. Sounds very fancy. All it is you essentially take all the predictions, or all the real values, subtract the predictions. So these are the difference between the predictions and the real values. You square it. So that's where the squared comes in. Then you take the mean, right? That's where the mean comes in. And then you take the square root, and that is where the root comes in. So this is the formula for RMSE. It's exactly as it sounds. So I've gone ahead and set up a function that does that for us. So here we take in the eval pred. So this will be what we get in the training process. It's essentially a tuple of logits and labels. So we're going to want to squeeze those, make sure they are as compact as possible. And then this is the formula I just showed you. We take the difference, square it, mean it, square root it, and then we have the RMSE. So we're going to return that as a dictionary because that is what the documentation says to do, returning it as a dictionary. And that should compute a metric. So now that we have that, what are we going to do? I guess now we just need to set up the training process and then we're good to go. So not too much, not too bad at all, right? So training arguments, or even before that, let's just make the trainer. So the trainer is going to equal a trainer, and this is a trainer by Huggingface. It does all the training heavy lifting for you, and is also fairly customizable if you want to add callbacks or anything like that. So it is quite nice. It's, yeah, I guess kind of the equivalent of maybe what Keras has, where they do all the training for you, except for this is NLP specific. But the model is what we need to pass in first. That is the model that we made earlier. The train data set is the ftrain data set. The eval data set is the feval data set. I put F here, by the way, for formatted. That's what it's supposed to mean. I don't want to write out the whole thing. We needed to say what metrics we want. So what metrics to compute is going to be this function we had earlier for compute metrics. And then we need some arguments, which right now is none because we haven't set any up yet. So let's go ahead and do that. The training arguments are things like the learning rate and how long we want to train, stuff like that. So the training args equals training arguments. Honestly, I don't know why they have their own class for this. I feel like they could just use, like a dictionary, but oh well, it's fine. So I put together, I did some testing for you all and figured out what worked well, and this was what worked well for me. We have a name for the training args. Again, I really don't know why. Maybe I guess you can use different sets of training args. but we're going to train for 5 epochs, logging every 200 steps with a learning rate of 1e-4. I just figured this out by playing around with it. The 1e-4 is a good place to start usually. And then we're going to have a batch size of 8. That is essentially the most the Kaggle GPU can take care of. And then the evaluation strategy is steps. This just means we're going to run evaluation every so many steps instead of the alternative would be every epoch or something, or not at all. So now that we have these training args, let's pass them into our trainer and hopefully nothing breaks. Oh, warning, but that's fine. We can deal with warnings as long as it doesn't crash. So this is the real beauty of using this trainer now, right? We took a little bit of time to set everything up, not too bad though, but how do we train the model now? All we have to do is say trainer.train. That's right. Well, maybe it'll crash, but oh, there we go. Awesome. So we're training. It'll take roughly 15 minutes. That's a bit long. So what I'm going to do is show you all that it works by taking the logging steps down to 10, just so I can demo this. So it will log faster. So 5 steps in already. Come on. Okay, so now it's running the eval over 36 steps. And there we go. Step number 10, we get our training loss, our validation loss, and our RMSE. Very, very awesome. So this is really all we need. Once this is done, and I'm going to stop it very early here just so I can do a demo, but you should let this run if you're submitting this. But all we have to do is say trainer.evaluate, and this will evaluate our model. So we can give it a second. It does have to run over. Oh, there we go. That was pretty quick. And it gives us the eval RMSE and the eval loss. Cool. Not too bad, right? So what the final thing we need to do, right? We made our model, assuming we let it train for a while, and I'll show you the results after this. But the final thing we need to do is submitting our model. And it's pretty simple. The way you do that is we just need to make a submission file. So we run the predictions on our test data set. So this will do predictions. I can go ahead and show you. If we run the, oh no, F-test data set is not defined. Did we not define it earlier? F-test data sets. Well, let's just define it right here. F-test data, or I'll do it on a new line. So F-test data sets should just equal F-test data sets, or sorry, this is F-test data set. Sets 0. Data sets. No. Oh, wait, no. I know what's wrong. I know what's wrong. It should be, gotta index this. Okay, cool. So we have our test data set. I don't know why it gets it as train. I don't know how to change that, but oh well. So we have, that should be our test data set. So if we go ahead and do the prediction now, there we go. So we have our target predictions. So we need to pair those with the IDs we get. And then we just essentially make a pandas data frame of the IDs and the targets. And then we save it as a CSV. So we run that, and on the right here, if we go to our working directory, you should see we have submission CSV, which is what we made. Let's go ahead and download it. If we open this baby up in a lovely notepad, you can see we have our submission. Awesome. And the way this works for this context, or this competition, is if you save this version, make sure you check always save output or save output for this version, and then you go ahead and save this. What you'll be able to do is submit this notebook to the competition. And once you do that, it will rerun your notebook. So it will take some time, but it will rerun your notebook on their hidden data set and grade your score. So I'm going to go ahead, and I'm not going to run the whole thing right now, but I did run it earlier. So I want to show you the score I got so you get an idea of what this method is capable of. So if we go to the common readability challenge in my submissions, ignore these two ones, I was just testing random things. But here you can see we got 0.588, which is not awful. If you look at the leaderboards, it's actually fairly low. There's a lot of people with this 0.46, 0.47, where we are all the way down here. But the reason I say it's not too bad is because all of these people are essentially just, there's an open source solution with a 0.46 score. It's not a simple one or anything. It's a very good solution. So that's why there's so many people with such high scores. But this is pretty good. We're getting somewhere, right? Now, there are still a lot of things we can do to improve this. So if you're interested in what those are and you're interested in how to improve your machine learning models, do consider subscribing to the channel. I do a whole lot of content like this, and it does mean a lot to me. Anyway, that is all I have for you today. So thank you so much for watching, and I hope to catch you all next time.